All right. As always, I just want to start with if you want to take a look at the notes that are on the tinyurl.com/Gabe tutoring. I posted the link the other day on the classroom. Same thing. Everything's set out for you so that way you can see all the notes and how the drugs compare and contrast, that sort of thing. So if you're ever wondering, oh yeah, what did he say for this? It's probably going to be in there. The big thing that we will do today is we're just going to do the most important information for each of the major classes, and then talk about how modifications on these structures lead to major changes in chemical activity. What's lucky about the second semester versus the first semester is that within every exam, within every class of drugs, things are a little bit more consistent. So, we're talking about opioids. Okay, all the opioids generally follow the same kind of idea, or the hypnosedative, usually follow the same sort of ideas as well. Next exam, when you guys get to all the psych drugs like antidepressants, antipsychotics, we'll see more of that as well. So if you felt the first semester was a bit random, hopefully this semester will be a little bit less random. But as always, let me know if something doesn't make sense. All right, first things first, we have to start and look at the 5-ring opioids. The biggest thing to bear in mind about the opioids is that we have 3 different backbones depending on what group these opiates are derived from. So, for example, the first group is the 5-ring opioids, and these came from morphine or opium. Opium is the latex from the poppy plant, and the major component of opium is morphine. So a lot of these 5-ring structures are going to be called our morphinians. I need to fix this. Come on. When we look at the morphinians, really what we are looking at is variations on each of the different rings. It's not necessarily important to know the numbering. It's not necessarily important to know, what the lettering of the 5 rings are. I don't believe that he really tests you on that, but it is important to know generally that when we talk about the 2 alcohol groups that we're talking about, the one that's on top, the one that's on bottom, that sort of idea. So we have 5 rings, A through E. And really what I want us to focus on is in ring A, we have a benzene alcohol, which we know is a phenol. Ring B, we have a 2-carbon bridge. So that's what carbon 10 and carbon 9 are. Carbon C is a unsaturated ring, which means that we have a double bond. On ring D, we have a what did I label wrong? Oh yeah, okay. Ring D is a cyclic amine, and then E is an ether bridge. Broadly, this is our plus an alcohol for C. Broadly, these are 5 main components. And so whenever we talk about changes to the opioids, we're always focusing on these 5 different positions. So let's take a look and let's see how these different things form. The first one that we're going to look at is morphine. Morphine is our quintessential morphinian. 5 rings, phenolic OH, tertiary amine, and then we have this alcohol on carbon 6. So we have our C3 phenolic alcohol. We should say 5 rings. Tertiary amine. C6 OH. So these 4 main components, by the way, this is carbon 3 and this is carbon 6. So what do these 5 components tell us? The 5 rings tell us that this is a morphine derivative. So this tells us the chemical classification. This is a morphinian. Our phenolic OH, this is a requirement for mu and kappa activity. So in order for a drug to bind to the mu and kappa receptor and cause some sort of activity, we need to have this OH on carbon 3. For a tertiary amine, this forms a basic salt. And because we can form a salt, it means that we have a better ability to form like an oral drug. And then finally, having this C6OH decreases lipophilicity, which of course we know decreases efficacy, right? So if you have less drug being able to cross through the blood-brain barrier, then you have less drug able to cause analgesia. Any questions so far? All right. So let's look at the modifications, because it's really from here that we start to see a bunch of different things. So let me grab a few different drugs. Oops. There we go. So codeine, hydromorphone, hydrocodone, and oxycodone. When we look at codeine, the only change that's in codeine compared to morphine is the presence of an ether. The fact that we have a C3 methoxy group, so a C3 ether, is going to decrease efficacy. Why would having an ether decrease efficacy if it also increases no, it doesn't. Why would C3 methoxy cause a decrease in efficacy? What do we think? It's a good thought. Not as potent. One of the big aspects here is that this would have to go through O demethylation, right? So this means that codeine is dependent on metabolism in order for it to work. The problem is only 10% of codeine actually goes through O demethylation. So that means 90% of codeine is being deactivated, whereas only 10% of codeine is actually useful. What does codeine turn into when it is metabolized correctly? Morphine. So what are you essentially doing when you prescribe codeine? You're prescribing very low doses of morphine. This is why codeine is not a very good analgesic, but it is a very good antitussive, because you need very low doses in order to get the antitussive effect. Hydromorphone, on the other hand, is instead of having that double bond and then that C6OH, what we're doing is we're using a C6 ketone. Unlike an OH, having this ketone plus no double bond, which is, I'll write it like this because it'd be easier, no double bond. This increases lipophilicity greatly. In fact, because of the lack of OH on C6, we now have a 5 to 10 times more potent drug. Why is it more potent? Because it's 5 to 10 times more able to cross the blood-brain barrier. So what's the result of having this change? Increased receptor affinity. Much, 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 much better. So combine those two ideas together, we get hydrocodone. So hydrocodone utilizes the C3 methoxy group as well as hydromorphone's ketone and double bond. So what does that mean in terms of what's going on in hydrocodone? This means that it would have more potency compared to codeine. Oop, actually, potency is the wrong word. You should probably say efficacy. Let's write it like this. I think this would be better. So because of the double bond, compared to codeine, which let me write these in a neutral color. Codeine, hydrocodone, and hydromorphone. Compared to codeine, hydrocodone is much more potent, more efficacious. Why? Because having that ketone increases lipophilicity and it makes it have better affinity. But hydrocodone would have less efficacy than hydromorphone. Why? Because remember that the C3OH is required for mu and kappa activity. So this would have to go through metabolism, but only 10% of it is being metabolized correctly. Good, 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 good. I'm glad. So what's going on in oxycodone? Well, oxycodone doesn't require metabolism, and it's utilizing the hydromorphone C6 ketone. The other difference in oxycodone is this C14OH. And what this does is it makes a drug a pure mu agonist. So no kappa activity. So same sort of thing. When we compare hydrocodone to oxycodone, who is going to be who would be more efficacious? Oxycodone. Why? Because it doesn't have to go through metabolism. I believe no, I think hydromorphone is, no, I'm wrong. Oxycodone is 100 times more potent or efficacious as morphine, and it's 10 times as potent as hydromorphone. Why is it more potent than hydromorphone? Because we have that increased affinity or exclusive mu receptor agonist activity. So, part of it won't be going to the kappa receptor. It's only going to stick to the mu receptor. Any questions about these? Does this clear up whatever you guys talked about in class? Yes, exclusively mu. Yep. Because, morphine, hydromorphone, hydrocodone, they're all going to have some kappa activity, very little, but there is still some. Whereas oxycodone is a pure mu agonist. Great. Moving right along. Oops. Now we're going to look at the antagonists. So just like what we saw with oxycodone, right? So what we're doing here is we're taking the structure of oxycodone, which there are 3 components to oxycodone. We have the C3OH, which, if you remember, is a requirement for activity. We have the ketone with the lack of double bond, which this is increasing lipophilicity. And then finally, we have that C14OH, which makes it mu only. One of the last aspects of the morphinians is that we need to have an interaction on this nitrogen. So what we do is we stick a bulky group. So by putting a really bulky group on the nitrogen, we block its ability to bind. To activate the receptor. So naloxone is utilizing this propene group, whereas naltrexone is using this cyclopropyl group. What should be noted about the cyclopropyl group specifically, or just in general, is that before I say that, what's important to note is that the combination of the C14OH plus the bulky group makes them pure mu antagonists. So naloxone and naltrexone are pure mu antagonists because of the C14. If that is not there, then we have a different group of drugs. All right, let's talk about that other group of drugs. See, I was telling you guys, much more consistent than last semester, right? Hopefully. Cyclopropyl. All right. Next up, we have nalorphine and nalbuphine. By the way, let me know if any of these drugs are not on your list, and then I will not talk about them. So one of the important things that we should do is we should figure out what the backbone is. So what mu agonist is the backbone of nalorphine? What mu agonist is the backbone of nalorphine? Yeah, this is a morphine backbone. How do we know? Morphine has OH and OH, and here we say we have an OH and an OH, and our C14 is a hydrogen. So is this a pure mu agonist? No, not at all. So what nalorphine and nalbuphine are mixed agonist antagonists. What we find is, again, we need our OH our C3OH to get to the mu or kappa receptor. We need to have we have our alcohol and double bond, which is going to decrease lipophilicity, right? Make it worse. But this time, what we're doing, instead of just having mu activity only, what we have is our big bulky group. So what ends up happening here is that the no C14OH plus a bulky group, what this does is that it decreases mu activity, but it doesn't touch kappa. I believe the reason is because kappa is a slightly larger receptor, so it can fit in there a little bit better. It's a little bit more forgiving, I think. So the result of this is that we have mu antagonism, kappa agonism. And so this means that we have weak analgesia. So what is the main difference with nalbuphine then? What is going to be nalbuphine's deal? Yeah, a couple of different changes. So we have our C3OH, so we're able to get to mu and kappa. Interestingly, we get rid of the double bond, but we keep the OH. So this is still going to increase lipophilicity. So the drug is still, sorry. This is still going to decrease lipophilicity. So the drug is not going to be able to get into the blood-brain barrier very well, right? But what we do is we add this OH to it. So what ends up happening here is that because of the C14OH plus the bulky group, plus this weird thing going on C6, the result here is that we have decreased kappa agonism. So again, it's still a mu antagonist, still a kappa agonist. But because of a combination of all these different factors, what we have is an even worse version of nalorphine. So who is going to have better analgesia? Nalorphine. Why? Because it has more agonism at kappa. So nalbuphine is worse than nalorphine, which is worse than all of our mu agonists. All right. Moving right along. We have a new class of drugs, chemical class. And here we're talking about our 6-ring opioids, which are called the oripavines. The biggest thing here is that you can see we have, I'll do it in green, this bridge. And what this bridge is doing, similar to the bridge that goes to the nitrogen, is creating our sixth ring. So similar in different ways, we have our C3OH required for mu kappa activity. We have our C6, no, uh, let me list them out actually. C3 phenolic OH, requirement for mu kappa. Forget. Let me double check how the numbering goes. Okay. 1, 2, 3, 4, 5, 6, 7, 8. No, that one gets skipped. 1, 2, 3, 4. No, I'm not sure. In any regard, here what we see on carbon 7 is a big alkyl group. What this extra group does is that it actually increases agonistic activity. Compare this with our other big bulky group, which is going to promote antagonism. The result of this is that we end up with the partial agonist nature of buprenorphine. So the tug of war that goes on between the large N group on buprenorphine and then the C7 alkyl group, that's what creates this partial agonist activity. And that's really the main component of buprenorphine. Our next group is our 4-ring and again, really at this point, we are just seeing the same trends over and over and over again. So our 4-ring opioids are our morphirans, not to be confused with the morphinians. And same sort of thing that we're always seeing, right? We have our C3OH, and this time, instead of having a ketone or a double bond, we just replace them with hydrogens. So again, we're increasing lipophilicity. The biggest thing is these drugs are more flexible than morphine. So the lack of that ether bridge, that 5th ring, is what increases flexibility. So it's able to fit into the receptor better. And so we get increased efficacy versus morphine. So quite useful. Same thing with dextromethorphan, where again, here we see the methoxy group, which means that we're going to have to do metabolism. So only 10% of this drug is going to be active. So what does that mean that we're going to be using dextromethorphan for? Answer is same thing as codeine, right? Antitussive, because we're only giving 10% of the dose, 10% of the dose of levorphanol. Then finally, with butorphanol, all we are doing is taking levorphanol, adding in that C14 for mu activity, but then we're adding this bulky group. And so just like we saw with nalbuphine and the mixed agonists, we get mixed agonist antagonist activity. So again, that kind of we're increasing affinity, but then we're blocking it off. So this is how we get that kind of tug of war again between them. Not terrible, right? Not too bad. All right. So where we have to go from here is our non-morphine derived drugs. So these are drugs where we are not relying on the original structure of morphine to kind of tell us what uh, the drug should look like. In other words, these are two rings and are called our phenylpiperidines. So the quintessential drug that we have is meperidine. Essentially, what we've done is we've stripped down morphine to its raw components. So instead of having A, B, C, D, and E, all we kept is the important aspects of the drug. So on group A, or ring A, we kept the benzene ring. So here's where A would have been. And then the only other one we kept is the nitrogen ring in the form of piperidine. And so what this is going to do is this is going to bind into the mu receptor, creating our salt link that's required. What's important to know about when we have these two ring, what's really driving the activity is our N-methyl group. This is what's creating our mu agonist activity. Uh, moving right along. two different drugs, diphenoxylate and loperamide. Same sort of situation where, again, we're keeping ring A and E. So here's ring A. Here is ring E. The difference is here that the is this a oop, it just yes, okay. The big thing here is that with diphenoxylate, it is used for its peripheral mu activity. And this is actually something we should talk about. In these drugs, such as loperamide, I think it would be here, and with diphenoxylate, the biggest thing that happens with them is that they form what's called a Zwitter ion. What ends up happening is that these drugs have a positive and negative charge at the same time. So overall, what is their charge across the entire molecule? Neutral. But they have a positive zone and a negative zone. And so what this means is that they are peripherally locked. So unlike all of our other drugs, which are able to cross the blood-brain barrier, these drugs are permanently charged. So they're not able to get into the bloodstream. They're not really able to get into the bloodstream. No, they're not able to cross into the blood-brain barrier. That's the biggest thing. Similar, but in kind of going the opposite direction. So instead of making the drug so bad at being absorbed, we're making the drug so good at being retained or crossing the blood-brain barrier. So again, we have ring A and ring E. But what's interesting here is that instead of having that ether, what fentanyl uses is this bridging nitrogen. What this does is that we increase activity as well as affinity hugely. So because of this nitrogen here, fentanyl has a ton of agonist activity. In order to get it into the brain, what we do is we use a very, very large, very lipophilic chain. So a large nonpolar group greatly increases blood-brain barrier penetration. And so this is actually the key component of fentanyl. Fentanyl is not a morphinian, so it doesn't have that, huge activity that we would expect of something like oxycodone. But because of this combination of this really strong pull on the nitrogen, where it really wants to bind into that receptor, and then adding this benzene ring, we're able to get fentanyl to do what we want. Going along the same sort of idea is methadone. So that idea of having these big, bulky, nonpolar groups in order to get it into the brain is what methadone is relying on. So large nonpolar groups increasing blood-brain barrier penetration. A, E. Any questions about these? All right, sweet. Next. So the barbiturates, the benzodiazepines, yeah, they really did. Once you start deleting rings, things start to twist out, and then it gets um, a bit nuts. Different stuff like that. Uh, da, da, da. All right, barbiturates. When we talk about barbiturates, the biggest thing here is really how long they are lasting in the body. All of them are all of them have very, very similar activities. They all kind of basically do the same thing. But really what the biggest difference is what we are connecting into carbon 5. That's really what is determining the difference between these drugs. So for our carbon 5 groups, we have a couple of different choices. The first is that we can have aliphatic groups, which if you remember, these are our straight chains. The key aspect of aliphatic straight chains is that we can do aliphatic hydroxylation. When we talk about aliphatic hydroxylation, the longer the chain, the faster the metabolism. The flip side to that is aromatics. So think of benzene. Even though benzene is big, 6 carbons, aromatic hydroxylation is still a slow process. Benzene is a very, very stable molecule. So trying to add an OH onto it can be really difficult for an enzyme to do. So it's still a slow process, despite benzene being larger than different chains, right? And we'll see that in just a second. So a couple of components. One, you need to have the barbiturate backbone in order to have your sedative hypnotic activity. And really, the difference between the different barbiturates is what you are binding onto the bottom of the drug. So the first one that we are going to look at is all of our long-acting drugs. So barbital, butalbital, and phenobarbital are 3 long-acting barbiturates that at least I have on my list. When we look at barbital, what we see is that the drug is only 2 carbons long, right? We have an ethyl group. So what this means is that we have a very, the drug is, what's the best way of saying this? Aliphatic hydroxylation is very tough on this drug. So what we end up getting here is we get a long metabolism as the body tries to stick an OH on the on our ethyl group. It's very tough for it to do it. Compare this with butalbital, which really same sort of thing. We have 3 carbons, but we have this methyl group right in the middle, and that is making it hard for the enzyme to come in and to metabolize. So here we actually have an isobutyl group. Now you might be looking at this double bond, and just remember that double bonds won't undergo aliphatic hydroxylation. And then finally, with phenobarbital, again, we're utilizing that ethyl group. And here we have our aromatic hydroxylation, but it should be noted that only 60% of the time it's going under aromatic hydroxylation. So the body is still trying to use aliphatic hydroxylation despite the benzene ring being bigger. So what this tells us is that aromatic hydroxylation, what this tells us is that benzene is a very stable molecule, right? That the body is almost 50-50 dividing its time between trying to target this tiny little thing versus benzene, which is much larger. The other thing to note is that having this benzene ring increases lipophilicity a ton, which means that when we look at the potency or the dosing needed for these drugs, what we can say is that we would need a lot more barbital than butalbital than phenobarb. Why? Because we have increasing lipophilicity. So we need larger doses of barbital than we do phenobarb. Any questions about that? All right. Moving right along, we have our intermediate acting. And here what we are doing is we are using some of the same concepts from the long acting, but then we're making it worse. So for example, in pentobarbital, we're using the ethyl group that is hard to metabolize, but then we're adding in this really long chain. Same thing with secobarbital. We're using this double bond, which is not going to go under aliphatic hydroxylation, but then we're adding this really long chain. So one chain is very bad at metabolism versus another chain is very good at metabolism. And hopefully you can see the pattern, right? Two bad chains, one bad chain, and now we're going to get into our short acting, which is two very good chains. So we'll talk about thiopental in just a second. But really, we should focus on hexobarbital. The difference in hexobarbital is that this is not a benzene ring. It's essentially a giant six-membered ring. This is a huge group. So we have a huge aliphatic group, meaning that hexobarbital is very, very, very easy to metabolize. And so it has a very, very, very easy time being eliminated from the body. So that's a key component of hexobarbital. What's important to note here is that despite having this tiny methyl group, hexobarbital is still easily metabolized. And really what this is that hexobarbital is just, this hexene group is just a massive, massive, massive group. Thiopental is utilizing the sulfur group. And what this is doing is that it is increasing the lipophilicity of the drug a lot. Specifically, with the action of the sulfur, this is actually going to increase the rate of metabolism. Think of the ring as a giant, massive alkyl group. And just remember that this is not a benzene ring. This is a cyclohexyl hexanyl ring. And then in thiopental, it's really the fact that we have this free sulfur that allows it to be metabolized very, very quickly. And then, of course, we have our easy to metabolize pentyl group and our hard to metabolize, but doesn't really matter, ethyl group. Not too bad, right? Oops. Oh, look, we're done with barbiturates. Benzodiazepines. Benzodiazepines have the same benzodiazepine nucleus, where we have kind of two major components to kind of think of. The first major component is that we have this phenyl group on carbon 5. So our C5 phenyl group. And then the other major component is that on carbon 7, we have an electron withdrawing group. Most of the time, this is going to be chlorine. And just to make this really, really simple so that way you guys can have it in your notes, when we talk about the duration of action, really what it is that if you have no C3OH, you are considered long-acting. So on carbon 3 here, we're going to see if there's an OH. If you have a C3OH, you are considered intermediate acting. And then on carbon 1 or carbon 2, if you have an methyl group, then you are considered short acting. And that's really the difference between these drugs. So, taking a look at the first group, our long-acting benzodiazepines. So, we have our C5 phenyl group, C5 phenyl group. This is a requirement for benzodiazepine activity. We have our, did it in blue? We have our C7 electron withdrawing group, which in this case is chlorine, which is another requirement for benzodiazepine activity. And then finally, what really tells us our rate of metabolism is if we have a what's it called? A OH at carbon 3. Oops, this should be no. Sorry, my bad. No C1 or C2 methyl. That's my bad. So if there is one, if there isn't one, then you are short acting. What's important to know about how benzodiazepines work is that we rely on the activity, do it in green, of this nitrogen. What ends up happening here is that in order for, in its current form, this is an inactive drug. What needs to end up happening is for it to undergo N-demethylation. So we actually need this methyl group to be removed in order to get our active form. So what this means is that drugs like diazepam, clorazepam, these are prodrugs. They need to be metabolized in order to become active. Taking a look at our next set of drugs, our intermediate acting, we have oxazepam, lorazepam, and temazepam. And here we're going to see some of the quintessential aspects that have just been missing so far. So again, to look at oxazepam, we have that C5 phenyl group, which is required for activity. We have that electron withdrawing group that is also required for activity. But the difference is here that oxazepam has this C3OH. What this means is that oxazepam is going to undergo direct phase 2 metabolism. That's going to speed up, that's going to decrease the duration of action, right? If we can go directly to phase 2, the drug is going to work more quickly. Or, sorry, it's going to last a shorter amount of time. What's also important to note about oxazepam is that the lack of the methyl group means that oxazepam is an active drug. Looking at lorazepam, same sort of thing. We have our phenyl group, we have our chlorine, C3OH, which makes this faster metabolized, and we have no methyl group, which means that it's in its active form. The difference with lorazepam is that we have an extra chlorine. Chlorine, as we talked about earlier, is an electron withdrawing group, and this is going to increase receptor affinity. So which drug has better activity? Lorazepam. And then finally, really the only difference with temazepam is that temazepam is just the inactive form of oxazepam. So temazepam is metabolized into oxazepam. Can temazepam and oxazepam be considered metabolites of diazepam? Really good question. In order for diazepam to become oxazepam, it would have to get this methyl group, or sorry, OH onto this position. And as of right now, diazepam would not go through, it would not add that. Would it add? It can, but it would be very, very, very slow, which makes sense because it's a long-acting drug. So yes, yeah, those drugs can be considered metabolites. Yep, that's a good question. All right, moving right along. Our short-acting benzodiazepines are just taking the aspect of that having more space for metabolism means that we have a shorter acting drug. So same sort of things that are going on. We have our C5 methyl, sorry, C5 phenyl. We have our electron withdrawing group. We do not have our C3OH, so we can't do direct phase 2, but here we're also using fluorine, which again is going to increase receptor affinity. So what's the big difference with the short-acting drugs? Well, it's that this alpha methyl group, which I will write this in a light purple. This alpha methyl goes through a very, very specific fast metabolism where it becomes a carboxylic acid. So this is very, very fast. So in triazolam and midazolam, the fact that we have this aromatic group attached to this nitrogen means that we have very, very, very fast metabolism comparatively. All right. Any questions? All right. Z drugs. So similar, we know that the Z drugs and the benzodiazepines bind in the same place. And really what the Z drugs are doing is good question. I don't think it changes the onset, but let me check. Uh, yeah. So it's a really, really good question. If um, the aromatic ring in midazolam or triazolam, if that makes the drug act quicker. So if the onset of action is quicker. And what we see is that onset of action actually has nothing to do with the metabolism of the drug. What onset of action is linked to is its lipophilicity. So this is actually a better chart, this one here. So if we look at drugs like midazolam, which only lasts 1 to 2 hours, we see that the onset is about 5 to 15 minutes, depending on how it's administered, versus diazepam, which is working between, almost immediately, 0 to 1. And if we look at the lipophilicity of diazepam, it's much, 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 much higher. So lipophilicity is more about onset, whereas the half-life of the drug is more related to the metabolism. Does that make sense? Okay. Really good questions. All right. So for the Z drugs, where the benzodiazepines have that fused ring between the azepine, the diazepine, and the benzene ring, what the Z drugs are doing is that they're just using a different kind of fused ring. That's really all they're doing. So, and just to kind of illustrate this point, if I bring back this guy, again, what we have in the benzodiazepines is we have two nitrogens in a ring connected to an aromatic ring. Basically the same thing among the Z drugs. The difference is that because these drugs are not because these drugs are not well, honestly, because they're not benzodiazepines, they don't fit very well into the receptor, right? They don't have as much activity. So even though that they have very, very similar structure uh, in the fused ring, they just don't have as good of activity. And that's really all I have written for these drugs. Um, so all of them have a fused ring, but they don't have much activity because we don't use them that way. I thought I had a lot more to say about these drugs. I don't, apparently. Um, you said what was the other one? Anti-epileptics and seizure. No, and anesthetics. Where did we do anti-epileptics? Yeah, uh, yeah, they're not fun. Um, Luckily, there are some similarities because of the way that they work. Especially if you remember from P-col, a lot of them are acting on the GABA receptors, right? So because of that, they need to have similar structures to barbiturates, which are, the quintessential GABA drug. So the first anti-epileptic that we're going to look at is phenytoin. And what I want to do is I want to uh, compare and contrast phenobarbital with phenytoin. Now, phenytoin has a high dantoin backbone. So it is not a barbiturate, which has a barbituric acid backbone, but because it has a very, very similar structure, this is what grants its efficacy. So the fact that you have this uh, double bond oxygen to the nitrogen, then another double bonded oxygen, and a nitrogen. The other aspect of phenytoin is that we have two really, really big phenyl groups. And if you remember what we said earlier about having two phenyl groups, what does this do? What does this mean about the drug in terms of where it goes in the body? Am I showing the right screen? No. Oh, did I? How long have I been on the screen? Did you guys see this? No? Okay. Well, I didn't really write anything anyways. Um, did you guys see? No, uh if I'm not showing you a specific screen, I always want to be on the drawing screen. Were you able to see this? Okay. All right. Okay. So we only missed this little portion, which is just about the fuse ring. Okay. Well, that's annoying. Sorry about that. Anyways, so when we look at phenobarbital versus phenytoin, the biggest thing here is that we have this high dentoin backbone. The fact that we have the two phenyl groups is that we have very, very, very good penetration into the blood-brain barrier, into the brain, right? So this is where the efficacy of phenytoin comes in, is that we have it on the two phenyl groups. Of course, what this means is that we're going to have aromatic hydroxylation as pretty much our only metabolism. And based on what we learned about phenobarbital and aromatic hydroxylation, what do we think the duration of action of phenytoin is going to be? Do we think it's long acting or short acting? Exactly. Yeah, this is a long acting drug. About, I think it's about a day that it takes. Usually, usually it takes about a week to get to steady state. The other thing to note about this is that with very lipophilic drugs, is this drug going to be able to dissolve into the blood very easily, which is very hydrophilic? No. So what does the body use in order to help transport lipophilic drugs? Plasma proteins. Exactly. So phenytoin is one of the quintessential highly protein bound drugs. So in the exam, if he gives you phenytoin and another highly protein bound drug, you can say, oh yeah, these are going to interact with each other. Why? Because they're very, very lipophilic. Ethosuximid. Unlike phenytoin, which is using a high dentoin backbone, ethosuximid is using the imid backbone. So this imid backbone, again, is just what is creating the efficacy of the drug. That's really there is all there is to say about it. The problem with imids versus the high dentoin is that this is uh, much more easily metabolized. So this means that for ethosuximide, the duration of action is shorter than phenytoin. Now, compare its groups versus phenytoin. Who's going to be more easily absorbed? Exactly. So in ethosuximid, because we have very, very small groups, which means that we don't have very good lipophilicity, which it doesn't decrease lipophilicity, I should just say is poor lipophilicity. This means that we have decreased absorption. It also means that it's not going to penetrate into the brain very well. Now, who is more protein bound? Phenytoin, right? Because it has way more lipophilic than ethosuximid is. Any questions about that? Does this kind of demystify these drugs a little bit? Hopefully this is helping. All right. Valproic acid. So stepping away from things that we previously have talked about, valproic acid. Valproic acid has a very special place in my heart because it has a very interesting way that it was discovered, which I will talk about at the end because I'm sure people just want to know about what they have to know for the exam. But remind me and I'll talk about it. Valproic acid, really the big component of this is that it has a carboxylic acid. That's what it is, right? So the other thing that I will just show you real quick. Will this work? No. Here is GABA. When we look at valproic acid versus GABA, what we can see is that it has very, very, very similar structures. The difference is that valproic acid is a GABA potentiator versus GABA, which is, of course, activating the different receptors. But it's just an interesting kind of overlap that happens between them. Whereas GABA kind of forms the Zwitter ion, and valproic acid is, literally just a very, very simple drug. A couple of things to note about it is that we have nice long chains. So that means its primary metabolism is going to be aliphatic hydroxylation and direct phase 2. Right? This drug as well, highly protein bound. Despite having this carboxylic acid, having these big long chains is going to require it to be carried by albumin. And for the most part, that is all there is really to say about this drug. Now, what is very similar to GABA is gabapentin. Gabapentin essentially takes the structure of GABA and locks the position of the carboxylic acid and the amine with this ring. One, two, three, four. Okay. The biggest thing about gabapentin to remember is that the carboxylic acid here will form a negative charge, whereas the amine will form a positive charge at the same time, which means that gabapentin, when it's in our body, forms that Zwitter ion, which again, this is when the molecule itself is charged, but the overall charge of the molecule is neutral. So it has a negative zone and a positive zone, but overall it is neutral. What this means is that gabapentin is very, very poorly absorbed. And so this is why you see doses of gabapentin that are in the thousands of milligrams. It's also why people get, 540 gabapentin a month. It's really annoying to count. I know it all comes together, right? Oh, it's awful. Absolutely awful. Similar, where we are taking GABA, but we are modifying the structure slightly, is pregabalin. Really, the utility of this is that we are still using the negative zone and the positive zone. So we still have the Zwitter ion, which is decreasing absorption. But what we have going on here is that we're adding this isobutyl group. And I don't have any way of confirming this, but I'm pretty sure that pregabalin was just a way to grab a structure and hold on to it. I think they were taking gabapentin and just using the utility of it. Yep, essentially. Same thing with vigapitrin, Zwitter ion as well. Another GABA derivative. And then really the only one that is very different is tiagabine. Tiagabine, again, it has its Zwitter ion component. But what it's doing is that we're adding on this big bulky group. And what we know about things like carbon and double bonds and sulfurs is that this is greatly increasing lipophilicity. So you get, compared to pregabalin, vigabatrin, gabapentin, you have very good oral absorption. So the doses of tiagabine are much, much, much smaller. Yeah, less counting. Exactly. Mm-mm-mm. Trying to think if there's really anything else among these to talk about, any connections, and there isn't really. Um, there isn't, because they don't do anything, and all I have is yeah, Kepra. It is uh it's a good question about Kepra. Is it it's not a GABA derivative. Um it's kind of in its own class, butyramide. Um and I'm just trying to think in terms of the time we have remaining. Um, da, da, da. I didn't even do the notes for this. This is where you can tell where my brain was in fourth year, that I did just took the notes on anesthesia and I didn't bother creating anything because I was done at that point. I didn't want to do it anymore. Studying for the exam. Okay. Let's wrap up here. Um, and just because I don't really have anything to add for the other drugs. Um, what I will say is that for the other anticonvulsants, for me it was on test two, so just go ahead and double check those. Um, but again, I really didn't have anything to say about them, other than just like a short description of what they were. Um, I am going to take a look at the anesthesia. We'll probably do that tomorrow very quickly, just so that way we can kind of get that out of the way. Um, did he go very much into blood gas partition coefficient or not really? A little. Well, it's more of a pharmacology topic. I'll take a look at what he put in the packet and see. Um, I didn't take a lot of notes on it when I was in the class because it was covered in exam one of PCall. So by the time I got to this, I already knew about it. Um, I'll take a look. Um, tomorrow I will post questions for you. Um, and then this weekend we will start Viro. Yeah, I remember him doing really, really like, well explaining that as well. Which is good because it's a really confusing thing if it's poorly explained. Last thing I will just remind you, in case if you don't see me tomorrow, is if you go again to the Gabe tutoring link, um, there is this study guide on all the different stuff in Viro. I have a very, very, very easy way of demystifying this all for you. Don't worry, I got your back. This looks very scary, but it's actually a very helpful tool for remembering all the different drugs, um, all that good stuff. And then that's exam two. All right. I will see you tomorrow. If you have any questions, let me know. All right. Take care.